Hello, followers of my YouTube channel. Welcome to today's tutorial. Last time we have seen about QSWAT, starting from watershed delineation up to that of visualization. So today we will see how to start calibrations. Okay, we will see how to start or how to do calibration methods. Basically, there are two types of calibration methods: the manual calibration as well as the automatic calibration methods. Alright, so today we will see how to use manual calibration. Alright, last time we have seen about the visualizations. Okay, so if you have opening or open your project under this visualization, and we can give your saved simulation here. Alright, simulation before calibration, and I would like to see the relation between the simulated and observed stream flow under the reach. Since I have a data from 1993 up to 1997, yeah, 1997, and let me select it from this one. From the plot you can provide the observed data, right? The observed data. In addition, you should have to select the sub-basin output, the sub-basin at the outlets of your watershed here. And for my case, this one is a sub-basin as outlets of the watershed, and I would like to visualize the flow out here. Let me add here, and already I have provided the stream flow from my data. This is the observed stream flow. Yep, and you should have to provide from this and add the observed data, and let us see the plot. Yeah, for instance, let me replace under this. Okay, therefore you should have to visualize your these simulated and observed stream flow hydrographs in such a way. And actually you can also view the statistical parameters that help us to measure your model. Yeah, the Pearson correlation coefficient is this much, and the Neistat efficiency is this much before we are going to do calibration. Therefore, in order to do your model be based performance, you should have to do calibration. Yeah, so the first way that you should have to do is manual calibration, and the other is automatic calibration. So the main difference between this manual calibration and automatic calibration is that manual calibration you can observe everything what you are doing. I hope that you get my idea. But on my automatic calibration, you have put some parameters, and you can only get an output, and you can actually don't see what's going on your model. Therefore, using those two calibration methods has its own advantage as well as disadvantages. For instance, when you are using manual calibration, you should have to check all parameters one by one. But when you see those automatic calibrations, you can provide a lot of parameters at once, and you can get your outputs after your calibrations. Okay, therefore those are the main difference between manual calibration and automatic calibration. Therefore today we will see how to work on manual calibration, and to increase the performance of our model, you should have to first install a tool which is called SWAT editor. Yeah, should have to install a SWAT editor. I hope you have seen that. Therefore, from this, let me open SWAT editor. SWAT editor. Okay. I hope. Let me open from this one. Yes. Sorry for this. Okay, so we have this SWAT editor, and under this SWAT editor, first you should have to say connect to your database. You should have to connect into your database in order to do a manual calibration. Therefore, connect to database. You should have to say that. Okay, and in order to do manual calibration, you should go to this. There is this manual calibration helper under SWAT simulation. Yes, there is manual calibration helper you can do, but before we are going to do that, go to this SWAT editor input, and you should have to select parameter from the sub-basin data or watershed data. Yeah, if you are interested in. Therefore, let me proceed with sub-basin data. Actually, you should have to consider what type of parameters should I touch in order to increase the performance of our model. Okay, you should have to take care of that before you are going to do manual calibration. Okay, therefore let me show you some highlights about techniques on SWAT calibration. And for instance, we may have uh, different issues. Yes, the first maybe say types of problems. Say type of problems, that means model failed to simulate some peak flows. Yes, I hope it is visible. Yeah, that means the observed data is under this. We have seen say types of observations, while the simulated is here now linear. Therefore, the main cause here is the rainfall station is not representative, one thing, and localized storm, that means no response is occurred under such conditions. And the other option may be there is malfunctioning gauges, or uh, the gauges for the stream flow as well as the precipitation may not be functioning as we want. Therefore, in order to do that, in order to solve such problems, we should have to use precipitation data from representative meteorological stations, one thing, and carefully review precipitation and flow data for the particular duration. So we should have to take those solutions in order to solve such types of problems. Okay, and the other maybe say types of problems. Okay, here is the simulated is above that of the observed. Yeah, model consistently over predicts the flow. That means the simulated value is greater than the observed value, means that the model consistently, that means throughout the time, yes, over predicts the flow, which tells has a high surface flow, So the model over predicts the flow due to different things. Okay, due to the curve number or the soil availability, and as well as the ISCO. Those parameters has high influence. Therefore, the first solution is decrease the curve number. If we are decreasing the curve number, we are reducing the simulated values because this SWAT works with SCS curve number method. Yeah, and it is directly proportional. Just the flow is directly proportional to that of the curve number. In addition, the soil available water content, yes, and the soil evaporation compensation factor. You should have to decrease the values of those parameters in order to reduce the simulated flow under such conditions. And in addition, there may be similar cases due to high base flow or too little evapotranspiration. This problem is also occur due to high base flow or too little evapotranspiration. Therefore, you should have to work on the groundwater parameters, groundwater revap mean, and GW QMN. Therefore, you should have to increase the values of this GW QMN as well as the groundwater revap, but you should have to decrease this revap mean. Okay, so those are the best solutions. And there may be time lag, the time lag on the peak. You see, for instance, this observed uh, flow, the peak is occurred before the occurrence of the simulated one. There is shift between the peak occurrence. So therefore, the simulated flow follows the observed pattern. You see, but lags the actual flow consistently. Here, the stream flow value may not be vary, but there is lag. Yeah. So this is due to time of concentration is too long. If the time of concentration is high or too long, such types of problem may occur. And the second is less than actual slope for overflow, overland flow. And the third may be overestimated surface runoff. I mean surface roughness. Yeah. So those are the main causes for such types of problems. Therefore, in order to solve such problems, we should have to take such solutions. For instance, just the slope for overland flow, this slope under HRU, adjust the Manning's roughness coefficient, yeah, OVN in subbasin or routing, and you should have to adjust the values of overland flow lengths, yeah, under subbasin or HRU if necessary, yeah. So you should have to take those measurements in order to take or in order to make your performance in acceptable range. And the other maybe here the here is some additional thing, yeah, that is the simulated flow over predicts the peak flow, but under predicts all other times. You see, this the simulated value is greater under the peak once, yeah, under the peak, the simulated is greater, but it is below in other cases. So this problem is the first one is too little base flow and too high surface runoff. Those are the two problems for such problems, and you should have to adjust the infiltration and interflow as well as base flow recession parameters. Those are the measures that you should have to take for such conditions. And there are additional things for the case of sediment calibration. So for today we will see those for the case of stream flows. And we have seen in our case from the visualization, we have seen that there are shift between the 1997, yes, and let me select the base the basin, the variable here, add, and let me add the observed. And if you see Let me use this as 6. Okay. Okay, you see, for the case of August 1993, August 1993, the observed one is under the simulated. The simulated is high in this case. Therefore, for this case, we may proceed to reduce the soil available water content, the curve number, and the likes. In similar way, here is the opposite of this one under August 1994. You see, and there is shift lag of time on the peak for the case of August 1997. Yeah, that means the simulated is occurred before that of the observed one, and in such a way. So we should have to take care, yeah, of touching which parameter is affecting our models. Therefore, in order to do that, you should have to go to this edit SWAT input under SWAT editor, and let me see the sub-basin data, yeah, and let me see, let me touch on the soil parameter, for instance, yeah, soil parameters, sub-basin. When you can select one of the sub-basin here, and the land use, one of the land use, one of the soil, that is possible. Okay, and say okay. And if you see the soil parameters here, we have the soil type is this one, the number of layer is 3, hydraulic grip is this one, this much, and the likes. Therefore, you should have to work on, for instance, let me decrease the available soil available water content. Yeah, let me decrease this one, for instance, 0.08. Let me see, and click on this extend editor to HRUs, then select all sub-basins, all land uses, all soils, and all slopes, and can save it. Okay, and let us close this one, and as well as let us select from the management, for instance, from the management parameter, um, let me increase this curve number. For instance, the curve number is now 71. Yeah, let me decrease this one. Yes, for instance, 65. Let us use this because you should have to decrease the curve number in order to reduce the simulated flow, and extend to all sub-basins, land uses, soils, and slopes, and save your edit. Okay, and let me touch one groundwater parameter here. From the groundwater parameter, one maybe this one, the groundwater revap. Let me increase this one to 800, for instance, 800. Okay, and let me reduce this one. You should have to reduce, but one at one place the simulated is under that of the observed. That is why I'm increasing. Therefore, this manual calibration is so tedious, yeah. So that is the reason why automatic calibration is better, since we are working all parameters together, and you can get our outputs at once. Let us decrease this one, for instance, 0.03, and let me extend to all sub-basin, land use, soil, and slope. Save our edit. So we have touched that the groundwater parameter. Yes, so you should have to rewrite your inputs. For instance, we have touched the soil parameter, so you should have to write the file here, then, and we have also touched the groundwater here, write the file, then and we have touched the curve number under management. Yes, write the file, done. So we have touched under those parameters. After that, we should have to run our model. Okay, should have to run our model again. For instance, from 1990 up to 2000, yeah, for the case of time. Therefore, my laptop is 64 bit, and I would like to see the monthly time step, and the number of warm-up period is 2. And let me set up our SWAT and run SWAT. Okay. Therefore, we can successfully run our we have successfully run our model, and then let us read our outputs here. Yes, this one export, done, and we can see the run SWAT checkup as well. But for our time, let us save this one, simulation number 2. All right, possible, and save your simulation. Yeah, successfully saved. So in order to visualize our data, click on this visualization, and you should have to select this simulation tool, and let me see the stream flow from 1993 up to 1997. Yes, and we have already selected the observed stream flow from this one, and the subbasin at the outlet is this much, and you should have to see the stream flow flow out, and it has plot. For instance, this one is 6. Good, save. All right, do you see the difference now? You can see the difference on the observed and simulated data. But if you observe the statistical parameters from the bottom of this one, the Pearson correlation coefficient is 0.58. It is reduced than that of the first one. And the nice statistical efficiency is as well less than 0.5, 0.6. And you see the influence of manual calibration is because our judgment is false. That's why the performance of our model is reduced than that of the first one. Therefore, this is the way of doing manual calibration under a SWAT, QSWAT. Okay, I hope you should have to take care on manual calibration, because you should have to goes to that of automatic calibration in order to reduce your effort on working with this manual calibration. You should have to take care of the parameters under this, what type of parameter you should have to touch, what type of parameter you should have to touch under such conditions, on the lag, on the overestimation, or the likes. Therefore, this is all about what I have, what I want to show you today. And if you have any questions, please put under the comment section. I will see that. In addition, if you are not subscribing my channel, don't forget to subscribe and share to your friends. All right, and it is enough for today. Thank you for your time. Bye.